In this video, I want to talk about source transformations. So far you have seen how we can use equivalent resistance for series and parallel resistive circuits, and also you got introduced to the concept of delta to Y or pi to T conversions that could help us sometimes to simplify our circuits. So source transformation is another technique to do that. So basically, let's just take a look at these two circuits here. So we have, for the one on the top, we have an independent voltage source with value Vs, which is in series with a resistor with the value R. For the second one, we have this independent current source with the value Is, which is in parallel to a resistor with the same value as R. So now let's just assume for these two configurations, I connect a load resistor, I call it RL, between terminals A and B. So what should be the relationship between the voltage source here and this current source? So we can say both of these circuits affect this RL the same way. So as you can see, the value for the resistor that we are using in both of the circuits is the same, R, right? But we don't know what is the value for Vs, or we don't know what's the value for our Is. Or more specifically, we don't know the relationship between Vs and Is. If we can know the relationship between Vs and Is, if we have anywhere in another circuit that we have a voltage source in series with a resistor, we can easily convert it to this configuration if it helps us to simplify our circuit, or vice versa. So the thing that we are looking here to solve is that in terms of this terminal behavior, A, B, that we have here, these two circuits, we want them to act the same way. So how that can be done? If the current that goes through RL, I call it here IL1, and for this one I call it IL2. So if these two currents are exactly the same, that means that the voltage across RL is going to be exactly the same in both of them. So let's just start from this point and trying to find the relationship between Vs and Is in these two circuits. So what is the current IL1 for the first circuit? So for the first circuit, if we have this configuration, Vs, R, and RL all in series, the current that goes through RL is basically the current that goes through R. And since we have two resistors that are in series, the equivalent resistance is the sum of the two. So using the Ohm's law, we can calculate the current as Vs divided by R plus RL. So that is the current that goes through resistor RL in the first configuration. So now let's just do the same for the second one. For the second one, if you remember from before, this is an example of a current divider circuit. So for a current divider circuit, if you remember, we said that the resistance that the amount of current that goes through each one of these resistors depends on the other resistor, not the actual resistor itself. So what does it mean? It means that, for example, if we have RL here and R here, if R is very, very large, that means that more current goes through RL. or if RL is very large, that means more current is going through R, right? So if you refer to the actual equations that were derived using Kirchhoff's current law applied in this node, we can see that the current that goes through RL is going to be R divided by R plus RL multiplied by IS. So this is the current that goes through RL in the second configuration. So now for these two circuits to be equivalent, IL1 needs to be equal to IL2, or Vs divided by R plus RL must be equal to R divided by R plus RL multiplied by IS. So as you can see, we can simplify these two denominators from both sides of the equation. So in that case, Vs is equal to R multiplied by Is. So as long as this relationship is satisfied, these two circuits are completely equivalent. So let's just put some numbers. So let's just assume we have this Vs to be 15 volts and this R to be 5 ohms. So we have a 15 volt resistor voltage source which is in series with a 5 ohm resistor. So what is the equivalent circuit after doing the source transformation? So if we have Vs to be 15 and R to be 5, that makes Is to be 3 amps. So that means that the equivalent circuit is having an independent current source with the value 3 amps in parallel with a 5 ohm resistor. So as long as this relationship is satisfied between Vs, Is and R, we can say these two circuits are completely equivalent in terms of what RL sees from these two terminals. So this is a very useful technique, especially when we want to simplify our circuits. So let's just recap. Suppose we have RL connected between nodes A and B for both of them. So RL is the load resistor that is the same for both of them. Then we calculate IL based off each one of these circuits. So for the first one, it is a very simple voltage source in series with two resistors. So the current is calculated using Ohm's law. For the second one, we use the concept from current divider circuit to calculate the current that goes through RL. For the two circuits to be equivalent, these two needs to be equal. So IL in both cases needs to be equal to each other. So that means that IS needs to be Vs over R, or Vs needs to be R multiplied by Is. So depending on the cases, sometimes you need to convert the first configuration to the second one, or you need to convert the second one to the first one, right? So depending on the situation, either of these two equations can be used. So now that we saw this, and we are still talking in terms of the terminal behavior at node A and B, right? So what if we have a resistor parallel with a voltage source? Does that affect our calculations or not? The other case would be if we have a resistor in series with the current source. Does that affect our calculations or not? So if we have this RP resistor in parallel with this voltage source, it doesn't have any effect in terms of what this RL sees. Why? Because the voltage across this RP, which will be the voltage between this one and, let's say, if we consider this to be the reference node, the voltage that is going to be applied to this part of the circuit is going to be exactly the same. As you remember from before, when we have two elements that are in parallel, the voltage across them is exactly the same. So when we have Vs connected between these two nodes, right? Having this RP in parallel with this voltage source does not affect what voltage we see across R and RL here. So what about having a resistor in parallel to, in series to this independent current source? So when we have this current source, let's say we want to write the KCL here. So since we have this independent current source, the current of this wire or this branch of the circuit is going to be IS regardless of whether we have this RS in series with it or not. So that means that it doesn't have any effect on the equation that we write for KCL for this node. So because of that, you can eliminate these when you are doing source transformation. Of course, that is only for simplification of the circuit, right? Not necessarily eliminating them equals they don't have any effects. So let's just take a look at this one. So for example, if you want to write down the KCL for this node. So you have a current that, let me just use this direction. So you have a current that goes through this voltage source. You have a current that goes through this resistor, and then you have a current that goes through this RP. So depending on you having RP in the circuit or not, the value for these two currents would change. For this one, it doesn't change, but for these two would change, right? Even though the effect of this RP on the rest of the circuit can be eliminated, practically it doesn't have any effect, but it doesn't mean that having this thing is completely useless, because having this resistor in parallel with the voltage source, that means that it is consuming some power or some current goes through it, right? If you completely eliminate that, current is completely gone, right? But in terms of what this RL is seeing, RP being there or not being there doesn't matter. So keep that distinction in mind. The same is applied here too. So if you have RL here, the current that RL gets does not depend on the value for RS. So that's why I say in terms of what RL is seeing, RS being there or not being there is equivalent. But it doesn't mean that the whole circuit is not going to be affected when you remove RS. For example, because this current goes through RS, we have a voltage across this RS with the value, so I can, instead of using Vs, I can write the voltage. So the voltage across this RS equals RS multiplied by IS. And if you have in your circuit any KVL written, you can easily see that the equation for KVL would be different, whether you have this RS or you don't have it. But in terms of the current that RL is getting, having RS or not having RS are both producing the exact same result. So such resistors don't affect the rest of the circuit and can be eliminated for the analysis. So it's like having less component in your circuit to simplify the equation. But when it comes to come up with the final answer, you definitely need to introduce them. So if you want to know the exact current that goes through this Vs, you need to have Rp. Or if you want to know the exact voltage across this Is, you need to have this Rs. Otherwise, the values are not correct. But in terms of what the rest of the circuit is seeing, having Rs in parallel with an independent current source, or having having Rs in series with an independent current source, or having Rp in parallel with an independent voltage source, they don't have any effect on what the rest of the circuit is seeing. So always keep that in mind. So in this video, you got introduced to the source transformation technique, and you saw a couple of examples on how you can transform a voltage and resistor series configuration to a current and a resistor in parallel configuration, and vice versa. And also you got introduced to some cases in which you can eliminate some components in your analysis for the purpose of simplification.